Hello everyone. In our previous video, we have completed the question number 70 and now today we are going to start topic 2, preparation and properties of haloarenes. And the question number 1, the decreasing order of reactivity of the following compounds towards nucleophilic substitution reaction. This question is very important. Therefore, I would like to explain you in detail and I will take your time a bit more. So first we should know the order of reactivity in SN2 reaction depends on its stability of transition state. If the transition state is more stable, then reaction will be faster. And which transition state will be stable? So if the reactant have minus I or minus M or both, then it can stabilize the negative charge of transition state. So for example, when we have nucleophilic substitution reaction, then let's imagine this is the reaction, and in this case nucleophile is attacking and halogen is leaving. If this R group has minus I minus M, then it can stabilize the negative charge through its inductive effects. So this is very important to understand that transition state carries negative charge. So therefore negative charge should be stabilized. So if the reactant has minus I or minus M effect, then it can stabilize the transition state. Therefore we have to see out of these four options which one has very strong minus I and minus M effect. In this case, first case, this is there is no substituents, nitro substituents. In the second case, nitro is at ortho position, and we know that nitro has minus I and minus M effect when it is present at ortho position. At meta, it has only I effect, and I effects decreases with distance. So I effects at ortho position will be more than at meta position. Now look at here. In case of 3, here is only minus I effect, and this one has minus I and minus M. Resonance effect is same at ortho or para position. Resonance effect doesn't change with the distance, but minus I effect is more at ortho and less at meta and more lesser at para position. If this is clear to you, then you can clearly say that the stabilization of the negative charge in the transition state will be more for 2, because in fourth case you have only minus I effect, no resonance, minus resonance effect is not there. So which one will be more reactive? 2 will be more reactive, and then third, because third has minus mesomeric effect as well as inductive effect, so third will be the less reactive as compared to 2, and then 4, and in the last one. So which one is matching? B is matching. Again, I would like to explain you. In the SN2 reaction, transition state carries negative charge. So stabilization of negative charge is very, very important for higher reactivity. And among these four options, 2 is stabilizing the negative charge more effectively, because in 2, minus I effects and minus M effects both are there, but minus I is more as compared to option 3, because in option 3, nitro is at para and therefore inductive effect is less as compared to at ortho position. But meta doesn't have any resonance effects, and same is here. And now, as I told you, resonance effect is same whether it is at ortho or para position, but inductive effects decreases with the distance, or here inductive effect is more and here it is less. And in this case you have only inductive effects, no mesomeric effects. Therefore this is the correct answer. This is very important question. If you understand this, then any questions coming from this topic, you can easily answer them. Moving to the question number 2, the major product of the following reaction. So the given reaction having sodium borohydride, which is a reducing agent, and it can transfer the hydride. So we have to understand that there are 3 reducing group: ketone, double bond, and imine, and we should know the properties, chemical reactivities of the sodium borohydride. Sodium borohydride reduce aldehyde to primary alcohol, ketone to secondary alcohol, and it can also reduce amine to amines, which functional groups sodium borohydride cannot reduce are ester, carboxylic acid, cyanide, nitro, halogen. These functional groups cannot be reduced by sodium borohydride, but it can be reduced by lithium aluminum hydride. Even lithium aluminum hydride can reduce all these functional group also because it is very strong reducing agent. Now let's see in the question. So as we said, it can reduce ketone. Yes. Can it reduce the double bond? No. It cannot reduce the double bond because this double bond is not in conjugation with this ketone. If it was like this, then it can reduce to give 1,4 reduction product. This is 1,4 reduction product. This is also depending on the cases. Not every time you will get the 1,4 reduction products. Okay, so this double bond will not reduce. Okay, this amine will reduce. Yes, so this is not the correct answer. This is also not the correct answer. Here, as we said that double bond can't reduce because it is not in conjugation with this ketone. So this is also not correct answer. The correct answer is this one. Okay, so let's talk about a little bit more about the situation in which double bond in the conjugation. For example, if you have this substrate and you are doing reaction with sodium borohydride, then you get 50-50% of 1,2 reduced product. This is 1,2 reduction product plus 1,4 reduction product. Almost 50-50% you get these two products. Since this double bond is not in conjugation, so it will not reduce. So correct answer is D. Now moving to the question number 3, the major product obtained in the following reactions. So the given reaction, if you see, is secondary benzylic halide. And in this reaction, tertiary butoxide is given. So tertiary butoxide is a bulky base. This is not a nucleophile. This is a base, bulky base, and heating at a high temperature. So it means nucleophilic substitution is not possible. Therefore, you can remove this option A, which is forming by the nucleophilic substitution if the reaction follow the SN1 pathway. But as we said, this is not a nucleophile. So option A, we can easily rule out. Now option B is forming by the elimination reaction. We will come on this option later on. Let's check option C. So option C is plus, and this is also the nucleophilic substitution. So plus minus, we cannot predict whether it will be dextrorotatory or levorotatory. So just by thinking this way, we can easily rule out option C and D. So what is left? Option B. So let's explain how B is forming. So since the base is bulky and it is very strong base as well, and it is under high temperature. So what is possible? The reaction is following either E1 or E2 mechanism. Since we have a strong base, so therefore we can rule out E1 pathway. So the reaction is following E2 pathway, and you can understand what is happening in E2 pathway. The base abstracting the proton, and at the same time halogen is leaving out and giving the alkene, and the trans will be the major product. So correct answer is B. Okay, now moving to question number 4. In nucleophilic substitution reaction, alkyl bromide reacting with the chloride in DMF and it giving alkyl chloride. So this reaction indicates that this is the substitution reaction in which chloride is replacing the bromide, and it is and it is SN2 reaction because inversion of configuration is taking place. So now the question, which of one of the following undergoes complete inversion of configuration? So for complete inversion of configuration, first of all, the compound must have chiral center. So let's see. In option A, if you draw, so carbon have hydrogen, bromo, and then two phenyl group. So it does not have chiral center. So we can't talk about inversion of configuration in this case. So ruled out this option. Next one is two hydrogens are there. This is also not chiral center. So ruled out this option. Now option C. In option C, carbon is attached to hydrogen, methyl, bromo, and phenyl. Yes, here we can talk about the inversion of configuration. Let's check option D. In this case, we have carbon have one phenyl and methyl. After that, this bromo, and then again phenyl. So again, this is not possible because it has two same group. So this is not chiral. So only chiral compound is C. So therefore inversion is possible only in C. So the correct answer is C. Now moving to the question number 5. This question is very interesting. Compound A, this is the compound A formula, gives a yellow precipitate when warmed with alcoholic AgNO3 silver nitrate solution. Oxidation of A gives an acid. So oxidation of A, after oxidation it is giving B, which is an acid, and then this easily forming the anhydride on heating. Identify the compound A. So let's look at the first option. So after seeing this option, we can easily say that this compound has one benzene ring. Okay, now how many carbons? 6 carbons are there. So we don't know what are the 2 carbons and where is the position of the halogen. So these are the missing information. Okay, so what is given next? Oxidation of A. So A on oxidation gives what is giving? Carboxylic acid. So for sure, this indicates that the benzene ring has methyl group, right? But we don't know how it is aligned. But we should remember that benzene ring having benzyl carbon and at least one hydrogen and anything else, one hydrogen and anything else attached on oxidation with the KMnO4 gives carboxylic acid. This we know clearly. So therefore, if you have methyl or ethyl, it can give you oxidation to carboxylic acid. This we clearly understand. What else is given? So next information is given that it can form anhydride. So remember that acid forms anhydride only when they are in a close proximity. When they are in a close proximity, and it can form 5-member or 6-member. Then only it can form the anhydride. So let's say when they are in a close proximity, they can give you anhydride like 5-member, and 5-member anhydride are stable. Okay, so now next important thing, it gives yellow precipitate when warmed with alcoholic AgNO3. Here I would like to inform you that alkyl halide, this is, let's say this is alkyl halide, when treated with silver nitrate solution, it could be aqueous, alcoholic, doesn't matter. So in this given case, it is alcoholic AgNO3. So AgNO3 is not a nucleophile. Okay, so what is happening? First, it will form the coordinate bond with the silver ions. So it can form the coordinate bond with the silver ions, and after that, nucleophile attack. So what is nucleophile here? Is alcoholic. So what is the formula of alcohol? This is the formula. So this is attacking as a nucleophile and giving you OR plus silver bromide as a precipitate. So we understand that alkyl halide reacts with the silver nitrate, gives silver bromide as a precipitate. What do you think about this case? Do you think it is possible in this case? So in this case, it is not possible. It can form the coordination bond. It can form the coordination bond with this bromo like this, but nucleophile attack at this position and breaking this bond is difficult. Formation of this is difficult because we know that carbon halogen has partial double bond character. We know that it has partial double bond character, therefore it is difficult to break. It means if halogen is directly attached to the benzene ring, it is difficult to break. So therefore, in this case, option B, you can see that it is directly attached to the benzene ring. So this is not possible. First reaction is not possible with this. Okay. So what about option A? Yes, first reaction is possible with this benzyl halide, because this is primary carbon and it has only single bond character, so it is possible to break. Okay, but oxidation of A gives acid. Yes, this is possible. It can give the carboxylic acids. But after that, can it forms the anhydride? Option A, you can get this kind of carboxylic acid, but it cannot form anhydride, because anhydride will be, it should be like this, and this is very big cycle and they are not in a close proximity. So this cannot form anhydride. Okay, let's look option C. So option C is also the same, like this part oxidize to give carboxylic acid, and this part is also giving carboxylic acid, but it cannot give anhydride. It can combine with the another molecule of the benzene ring to form the anhydride, but then formula will not be like this, right? So this is also not possible. So what is possible? Option D. In option D, this is possible that it forms the anhydride easily, because first you will get this kind of carboxylic acid, and then on heating you get this 5-member stable anhydride ring. Okay, one more time, I would like to tell you that anything on a benzylic carbon having at least one hydrogen can easily undergo oxidation to carboxylic acid. This is clear to us. So therefore, we can easily understand that this CH2Br can oxidize to carboxylic acid. And then methyl, we know that methyl oxidation gives carboxylic acid. But we have to choose the orientation of these two groups. And the best orientation will be D, because then only you can get anhydride on heating. So I hope it is clear to you now. Now question number 6. The Wurtz-Fittig reaction involves condensation of. So we know that in Wurtz involve the condensation of 2 alkyl halide. And in the Fittig reactions involves 2 aryl halides. But in Wurtz-Fittig reaction, it involves the condensation of alkyl halides and aryl halides. So, which is the correct answer? 2 molecules of aryl halides? No. 1 molecules of each aryl halides and alkyl halides? Yes. 1 molecule of each aryl halides and phenol? No. 2 molecules of aryl halides? No. So the correct answer is B. Now moving to the question number 7. Aryl fluorides may be prepared from arene diazonium chloride using. First option is the correct answer. Tetrafluoroborate on heating with diazonium salt gives fluorobenzene, and this reaction is known as Balz-Schiemann reaction, and the rest options are incorrect. Okay, now moving to the next one. The major product of the following reaction. So this is the benzyl halide, and we know that benzyl halide can show SN1 and SN2 reaction because it stabilizes the carbocation as well as transition state of SN2 reaction because of the phenyl having -I effects and -M as well. So we know that it can show SN1 or SN2 reaction, and we know that this is very strong nucleophile because sulfur has, whenever you see the negative charge on sulfur, it has high tendency to give electron density because of low electronegativity. And DMF, it means it is a polar aprotic solvent, and we know that polar aprotic solvent is used in case of SN2 reaction. Okay, so what are possibility here? So let's say if this phenyl sulfide attack, then this product is possible through SN2 pathway. This product is possible if the reaction is taking place from the same side. So we know that in SN1 you get retention. This is the retention product, as well as inversion. So only you are seeing only retention here, no inversion product. So this is also not possible. What about option C? In option C, they are replacing the fluoro. Do you think it is just it is impossible to replace fluoro? There is no logic behind it. Actually, there is a logic behind it. You can replace the fluoro, and this reaction is known as nucleophilic aromatic substitution reaction. So this is very well-known reaction. Don't think that like that. This is they just replace the fluoro without any logic. No, this is called nucleophilic aromatic substitution reaction. But in this case, is it possible to replace the fluoro? So let's understand. Actually, fluoro could be replaced if nitro was at para position. And in this case, if nucleophile attacks, then negative charge comes in the ring, and this negative charge can be stabilized by the nitro group through the resonance. So it goes here and then follow up. So in this way, you can draw for the resonance. You know what is those are the resonating structures. So and after that, this fluoro goes away and nucleophile comes. So this is possible if nitro was at para position, but in this case, it is at meta position, so it is not stabilizing the negative charge. Therefore, substitution only at this position is not possible. Okay, now, but it could be minor product. There is a possibility that it could be minor product. Okay, we can't rule out this one. What about option D? In option D, they are replacing both this one and this one. Okay, this is also possible, but what they did, they are showing retention of the configuration. Okay, and fluoro replacement also. So this cannot be the major product. This cannot be the major product. So what will be the major product? Major product will be A, because the reaction will follow the SN2 pathway, and due to the strong nucleophile and polar aprotic solvent, and at the same time, benzylic halide stabilize the transition state due to its -I and -M effect. Therefore, we can say that the correct answer is A, not B, C, or D. If you have any doubt regarding question number 8, please ask me in the comment box. Now moving to the question number 9. When phenyl magnesium bromide reacts with tertiary butanol, the product would be. So magnesium bromide, we should know that whenever you react the Grignard reagent with any acidic medium which can provide the proton, which can provide the hydrogen, so what is going to form? Hydrocarbons will form. So what will be hydrocarbons here? This, and this is nothing but benzene. So the correct answer will be A, benzene. Now moving to the question number 10. How many structures for F are possible? So in the given reaction, this secondary alcohol in the presence of acid losing the water molecule giving the F. So F for sure it is alkene, and then after bromination getting 5 products. Okay, so let's understand this reaction through mechanism. This is the secondary alcohol reacting with the acid. So first step is the protonation of the OH, we know that, and followed by the removal of the water molecules to give the carbocation. This is secondary carbocation. There is no possibility of rearrangement. So what is going to happen? Removal of the hydrogen. So this is, let's say, HA, this is, let's say, HB. So when HA will goes, then you get this double bond in the middle. If you remove the HB, then you get the double bond at the terminal position. So there is also possibility that you can get the cis geometry. So one is this, second is this, third is this. So how many structures of F are possible? 3. So let's go back to the problem and check which is the correct option. 2, no. 5, no. 3 is the correct option. For our understanding, we should also understand how these many products are forming. So they are showing 5 products. So let's try to understand. So if you do the bromination of these, we know that bromination is the anti-addition, and it leads to the bromination at both the double bonded carbon atom. Now if you see here, there is a one chiral center. So therefore there is a possibility of D and L enantiomer. So we get two products from here. Okay, now coming to the interesting part. So you have transalkene plus bromination. So what will you get? We know that you will get either meso or racemic mixture. But the trick to remember that, I told you in my last video how to remember this, and I always use a mathematical analogy. So what is this mathematical analogy? I want to tell you again. We know that this is anti-addition reaction, and we can call anti, let's call it trans-addition reaction. So I use my mathematical analogy, trans geometry minus trans addition gives 0. So 0 means meso compound, because meso compound has optical rotation 0. So it means I can understand there, therefore this will be meso compound and it will be only 1. Okay, now if you have cis geometry and it is bromination, which is anti, so cis geometry minus trans addition, you will get non-zero. So in this case you will have racemic mixture. So how much compound you will get? 2. Racemic mixture means enantiomers. You will get in this case also enantiomers. So 2 from this, 2, 1, 2. So total 5. 2 plus 1 plus 2 is equal to 5. So you will get total 5 products in this way. If you have cis geometry and let's say you have osmium tetraoxide, and we know that this is cis addition reaction. So in this cis addition reaction, you will have dihydroxylation, and this dihydroxylation, cis minus cis is equal to 0, so it will be meso compound. So this way I easily remember whether it will be meso or racemic mixture. I hope this is clear to you. Now let's move forward. Moving to the question number 11. The reaction of toluene with chlorine in the presence of ferric chloride gives predominantly. So this reaction is the example of electrophilic substitution reaction. So this is the structure of toluene, and when you react with the chlorine in the presence of FeCl3, then it generates the Cl positive as electrophile, and this electrophile attached to the benzene ring. And now we know that methyl has plus I effects, therefore it is ortho and para directing, and hence there will be a mixture of product chlorine at the ortho plus we know that para will be major product. Okay, so what are the options? Benzoyl chloride? No. Metachlorotoluene? No. Benzyl chloride? No. Ortho and para chlorotoluene. So the correct answer is D. If they were asking only one of the major product out of ortho and para, then para will be the major product. Now moving to the question number 12. Chlorobenzene can be prepared by reacting aniline with hydrochloric acid? No, because aniline on reacting with HCl just will give salt, nothing else. Cuprous chloride? No. Chlorine in presence of anhydrous aluminum chloride? No, this will lead to the chlorination of the benzene ring. Nitrous acid followed by heating with cuprous chloride? Yes, this is the correct answer, because when you react with the aniline with nitrous acid at 0 degrees Celsius, then you get the diazonium salt, and this diazonium salt can be decomposed by cuprous chloride to corresponding Cl. If you use cuprous bromide, then it gives bromobenzene. This is the example of Sandmeyer reaction. Okay, now true or false. So in question number 13, metachlorobenzene is an isomer of meta-bromochlorobenzene. So let's draw the structure first. So this is put chloro and this is the bromo. And in this second case, if you put first bromo and then chloro, so if you see these molecules are identical, so they are not isomer, and hence it is false statement. Okay, now moving to question number 14. Choose the correct option for the following set of reactions. So this is the reaction of this molecule with the Grignard reagent followed by hydrolysis gives Q, then treating with concentrated HCl. Okay, after looking the option, we can easily understand that this compound has cyclohexane ring, and this cyclohexane ring having oxygen. So after this, putting this oxygen like a ketone, then it satisfies this formula: 1 2 3 4 5 6 carbon, 10 hydrogens, 2 2 2 2 2, 10 hydrogens. So this is the formula of this. Now it is reacting with the Grignard reagent. So when it reacts with the Grignard, we know that Grignard is a nucleophile, and this alkyl will go here and then followed by hydrolysis to give tertiary alcohol, and this is the structure of Q. And after that, they are asking reaction with concentrated HCl. So in this case, concentrated HCl, what it will do, it will remove the water to give the carbocation like this, and this carbocation will get further attacked by the chloride because it is concentrated, so chloride concentration is very high, so it will attack here and gives CH3Cl, and this is the structure of S. So if you see S is this, yes, correct. And okay, so we have to actually draw all the structures because they are asking every structure T, R, U, and this is MCQ with one or more than one correct answer. So there could be more than one correct answer. So let's draw other structures. And there is a reaction of Q. This is the reaction of Q. Actually, its arrow is here with phosphoric orthophosphoric acid, and this is 20%. So it is providing the dilute condition, and in dilute condition, Q is the OH has OH group. So what is going to happen in this case, after removal of water, this gives the carbocation, and this carbocation will not get attacked by any nucleophile because PO4 is not a nucleophile. So what is going to happen? Elimination. So hydrogen from the beta position will go away and it will give more substituted alkene according to the Saytzeff rule. Therefore, the correct structure of R will be this, and then R is treated with the Rani nickel. So after treating with the Rani nickel, this double bond will get saturated and you will get hydrocarbon, and followed by bromination in the presence of sunlight. So this bromination will be radical mechanism. It will give bromo radical, and this bromo radical will go to the more stable radical, and tertiary radical is the more stable one. Therefore, the reaction will take place at this carbon. So this will be the structure of T. And now R on reacting with HBr in the presence of peroxide, so it will follow the anti-Markovnikov's rule, and according to this rule, hydrogen will go to the double bonded carbon which have less number of hydrogens, so it will come here, and bromo will be here. So this will be the structure of U. So let's check how many correct answers are there. So S is this, yes. U, what is the U? Yes, U is structure of U. So A is the correct answer. So B, in case of B, U is this, yes, this one is correct. And what about T? Let's check the T. What was the T? T is this one, yes, T is also correct. So A and B are correct. Let's see the C. U is this, no, this is not the correct one. S, what was the S? S was directly attached to the chloro, so this is also not correct. And D, in case of D, S was, yeah, this is not the correct structure of the S. Okay, so only two options are correct, A and B. This is the correct answer of this question. Now question number 15. Benzyl chloride can be prepared by toluene, chlorination of the toluene. So to prepare this one, this is possible only when you do the radical reaction. And for the radical reaction, you need chlorine in the presence of light. So therefore, only this is the source of the Cl radical, and rest of the reagents you can easily rule out. So the correct answer is C. 16. aryl halides are less reactive towards nucleophilic substitution reactions as compared to alkyl halides due to. Okay, so we know that aryl halides are less reactive towards nucleophilic substitution reactions because of the partial double bond character of this carbon halogen bond due to the resonance. So the formation of less stable carbonium ion, this is not valid because if this bond will not break, then it cannot form the uh, carbocation. So there is no sense to talk about the stability of carbocation. Resonance stabilization, yes, as we have seen, longer carbon halogen bond, this is not correct because this carbon is sp2 hybridized and due to which the carbon halogen bond is shorter, not longer. The inductive effect, this is also not valid. sp2 hybridized carbon attached to the halogen. Yeah, this is the correct. So B and E are the correct answer for this question. Moving to the question number 17, match the following. So in column 1, we have to match with the column 2 and they are saying that it can match with more than one item. So let's check it. So okay, this is the halide on reaction with, okay, this is all together actually, this is all together and this one is together with this like this. Okay, so what they are asking, this halides on reaction with ethoxide gives alkene. So this is E1 reaction, E2 reaction, even C1 reaction or first order reaction. So first we should understand that whenever you see primary halides, so there is a possibility of E2, not E1. And for E2 we need strong base. For E1 we need weak base is enough, and it's shown by secondary or tertiary halides. But in the given question we have only primary. So look at this, A is primary halides as we said, therefore it will match to E2 reaction. So A will match to Q E2 reaction. Only one option, it is matching to one option. Now let's look at the B. B is secondary halides, both are secondary halides. This is deuterium, instead of hydrogen this has deuterium, this has hydrogen. So secondary halides will give E1 mechanism. Therefore we can say that B is matching to P E1 reaction, and we know that E1 is first order reaction, therefore it will match to the S also. So first order reaction. Now look at the C. So this is primary halide on treatment with ethoxide gives ethoxides, and this deuterium labeled ethanol gives alkene, and in this alkene you can see that deuterium is coming on this carbon. What does it mean? So how it is possible? So let's look at this. You have CH2 Br, and after this you are getting alkene, and in this alkene the deuterium is coming at beta position, alpha position, beta position with the double bond. So this is possible only when the reaction is following E1 CB mechanism, because in this reaction the mechanism will be, first it will be the abstraction of proton by base to give the carbon ion, which is a conjugate base, and therefore that's why the reaction name is conjugate base. So it will form carbon ion like this, and this carbon ion can take deuterium from ethanol, this deuterium ethanol, to give you something like a deuterium level species like this. And after that another proton can be taken away and to give this carbon ion, and then followed by removal of this halogen to give you this deuterium labeled product. So hence this reaction is following the This reaction is following the E1CB reaction, and this is also first order reaction. So C is also matching to R, E1CB and S first order. So it is also matching to 2. This is also. Now let's look at the D. This species reacts faster than this one on reaction with ethoxide in ethanol. Okay, so this is the primary halides and reacting with faster than this. So this is also the example of E2 reaction, because this is, first of all, this is primary halides. Second reason, this is ethoxide is a strong base. Therefore, it will lead to the removal of the proton, beta hydrogen, you can say, and halides at the same time. Therefore, D is also following the E2 mechanism. So this is the correct matching. Now moving to the question number 18, assertion and reason type question. So what they are saying, statement 1, bromobenzene upon reaction with bromide. Statement 1, bromobenzene upon reaction with bromine in the presence of iron gives 1,4-dibromobenzene as the major product. So this is the example of electrophilic substitution reaction, and para is the major product because bromo halogens are auto para directing group. So this is the major product. So first statement is correct. Now statement 2, in bromobenzene the inductive effect of the bromo is more dominant, yes this is true, than the mesomeric effect in the directing the incoming electrophile. Inductive effect of halogens are dominating over plus M effect. This is true statement, but this is not the reason to direct the incoming electrophile. Hence statement 2 is incorrect in context of directing the group. In context of directing the group, it is incorrect. So the correct option is statement 1 is true, statement 2 is false. So C is the correct answer. Again, I would like to repeat. Statement 2 up to the half is correct, that bromo group is more dominant. Inductive effect minus I effect of halogens are dominating over plus M. This is true statement, but this is not true in the context of directing the incoming electrophile. So which effects directing the electrophile? The positive mesomeric effect of bromo direct the electrophile at ortho and para position. This is the correct reason. Hence, we can say that statement 2 is incorrect. Now moving to the question number 19, subjective problems. Give reasons for the followings. So on reaction with aqueous ethanol, this is the tertiary halides, and tertiary halides can decompose to give easily tertiary carbocation, and you will have bromide in the reaction medium. This bromide will take the proton from the ethanol to give the HBr, and this HBr will create acidic solution. But in case of this case, this carbon halogen bond has partial double bond character because it is directly attached to the ring. Therefore, breaking this bond is difficult, and hence this solution is neutral. Now question number 2, 7-bromo-1,3,5 cycloheptatriene exists as ionic compound, while 5-bromo-1,3 cyclopentadiene does not ionize even in presence of silver ions. Explain. So for this we should know the structure of the mentioned compound. So this is the structure of 7-bromo. This is this heptatriene. So 3 double bonds, triene, 3 double bonds are there. This is the bromo. This is the 7th position. So this exists as a ionic form. What is this ionic form will be? This is the ionic form. Positive charge, Br negative. Why it is existing in ionic form? Because this is sp2 hybridized after decomposing, and this can delocalize in the empty p orbital of this carbon. So therefore it is following 4n+2 rule, Huckel's rule. It is following cyclic planar and delocalized pi electrons. Hence it is aromatic in nature. therefore it is stable. This carbocation is stable, therefore this is can exist in the ionic form. But if you look another structure, 5-bromo-1,3 cyclopentadiene, so this structure will be like this, and if you decompose this one, then you will have this carbocation. This carbocation also have sp2 hybridized orbital. This structure can also show the delocalization of this positive charge like this, but still it doesn't exist because it does not follow the Huckel's rule. If you try to find the n value, so 4 minus 2 divided by 4, so n cannot be a fraction. Therefore, this is not following the Huckel's rule, and hence it is not aromatic compound. So therefore, it has high energy and it is unstable. Okay, now moving to the question number 20. Write the structural formula of the major product in the following case. So this is the example of Ullmann reaction. When you see the copper and aryl iodide, bromide or chloride, then it undergoes the coupling of the two species. So two molecules of this will couple and you will get this product. This is called Ullmann reaction. Okay, how will you prepare meta-Bromoiodobenzene from benzene in not more than 5 to 7 steps? So to prepare the meta-Bromoiodobenzene from the benzene, so let's write the structure of benzene and what we have to prepare. Let's write the structure of that also. So this is iodo and bromo at the meta position. So first what we should do nitration. So if we do the nitration, we know that nitro group is meta directing group, and hence we can bring the meta group. So bromination in the presence of iron bromide will give you this product. So now we have bromo at the meta position. We have to think about how to remove this nitro group. We know that this nitro group can be converted into amine by reaction with the tin HCl to NH2, and after that everything is very simple because we are very familiar with the Sandmeyer reaction. So we can do the Sandmeyer reaction by treating with HNO2 nitrous acid at 0 degrees Celsius to give diazonium salt, and this diazonium salt can be easily break down into by treating with potassium iodide, and then you will have this requested target. Now moving to the question number 22. Give reasons for the following. Aryl halides are less reactive than alkyl halides toward nucleophilic reagents. So we know that this reason of this reaction we know very well because of the partial double bond character through the resonance, which makes this bond very stronger, and hence nucleophile can't break this one. Question number 23. What happens when excess chlorine is passed through the boiling toluene in the presence of sunlight? So toluene, this is the structure of toluene, and the given example is the example of radical reaction. But if you pass 1 mole of the toluene, 1 mole of the chlorine, then you will get only monochlorinated product, and this will give at this position because benzylic radicals are more stable, and since you are passing excess of the chlorine, therefore all these hydrogens will get replaced by chlorine, and then you will have 3 chlorine on this benzylic position. So this will be the correct answer. So this is the all. We have almost solved 100 questions from this haloalkanes and haloarenes series.